So again, well, I wish a warm welcome to everyone, especially to Patrick Michel for this new AC webinar. So for those of you who are not really familiar, we have now a cycle of monthly webinars on all sorts of topics in this Game Changer series. So today it's a real pleasure to have with us Patrick Michel, who is director of, what is the French translation, the English translation? Well, senior astronomer at the, researcher at the Observatory of the Côte d'Azur in Nice. He's definitely a specialist in asteroid observation and simulation. He's also a global fellow at the University of Tokyo, the School of Engineering, and he has authored many papers dealing with the characterization and study of asteroids. So we're really looking forward to have a different topic. So we've had a few talks on astrophysics in the last few months, one on climate, and the next one, this is just to let you know, the next one will be given at the end of the month by Judith Lean from the NRL and LAS Observed laboratories in the US on long-term reconstruction of solar activity. If you have questions, please write them down in the chat and we will go through your questions. So if any questions arise, don't hesitate to write them down in the chat. And hopefully we'll have enough time to answer many of them. With that, I think it's time to start. So Patrick, the floor is yours.
Okay, so you see well my screen?
Yes, perfect.
Okay, so thank you very much for inviting me to give this talk. We live a fantastic era for asteroid missions, and I will try in about 45 minutes to show you the successes that we had so far, the challenges, the surprises, and everything that happened until now. So first of all, I need to recall why we study asteroids, and I think this explains why we have so many missions that have been done and so many missions that are in development, which is really great for the future. So it's because there are many reasons to study them, and despite that these reasons are very different and involve very different communities, they essentially need the same knowledge. And so, of course, the first reason is a scientific reason, because we think that they are the best tracers of the formation and history of our solar system. They are small enough that they were not really heated, and therefore their material records the original composition of the ingredients that were there when the solar system was formed and that built the planets. Moreover, they are also possibly linked with the emergence of life on Earth. So this is a really important scientific reason to explore them. Another one is linked to planetary defense, and that will be one of the main focus of my talk. So some of them represent a risk of impact, and therefore we need to understand them in order to be able to mitigate this hazard. And then there are another reason, which is that they are possible resources for further exploration in the solar system. In other words, in order to instead of taking the energy from Earth, because they contain hydrated minerals, you could use the water to make new propellant on site and go further away. And again, we need to understand their composition and their physical properties. So that's a good thing, because whatever the primary objective of a space mission to an asteroid, the knowledge that we get feed the three communities which are interested in these three topics. So that's possibly explain why there is this kind of a great enthusiasm worldwide for asteroid missions. So talking about the hazard, let's talk a little about it. So of course, the impact risk decreases with the size of the object, fortunately, because we have less numerous larger asteroids than small ones. And you can see here the frequency of impact as a function of size is really small for the one that can do damages at a regional level for 140 meters to global level at 1 kilometer in size. So we could say, okay, we have no reason to be worried, and effectively on our lifetime, for the moment, we don't have any identified threat. However, we know that it will happen on the long term, and we also know that we cannot easily improvise if something happens, because it's a multi-parameter problem. We need, as you will see, many things to be known in order to be able to be protected, and therefore it's better to be ready before we need it. Plus, this risk has an advantage compared to many other natural risks. We have means to predict and mitigate this risk, which we just need to implement without any need for a breakthrough in technology, etc. So in other words, we are now working on this in order to offer a robust plan to the future generation that will eventually have to face it, with no reason to be worried on our lifetime in principle. So for this, we need 3 actions, which are actually developed in parallel. The first one is the prediction. Of course, we need to understand what is the risk, where are these objects, and whether there is one which is really threatening us. And for this, we have telescopes that try to do the inventory of all threatening objects and estimate their impact probability. So we have discovered most of the objects which are larger than 1 kilometer in diameter, and none of them threaten us for the next century or so, which is the time of predictability of our calculations. And now we are trying to do the inventory of all the objects larger than 140 meters, which is a threshold for regional damages. There are about 16,000 objects larger than this. We only know 40%, so it would take decades to do it from the ground. Fortunately, NASA will implement the NEO Surveyor Space Telescope, which will do the job in 10 years once launched, and it should be launched in 2028. In parallel, we have mitigation, which is characterizing the physical properties of these objects in order to design a space mission that can deflect them with a proper efficiency, and also validate this kind of deflection mission so that we know which one works, for which we are ready, and for which one we need to make more efforts. And then we also need an international coordination, because if we predict that an object is coming to us, then we want to be organized worldwide and make sure that we have a coordinated response at international level. And for that, we have working groups under the United Nations at the Committee of Peaceful Use of Outer Space that try to develop some protocols which allow us to know what to do as a function of the probability, the size, etc. So today, because we have a limited time, I'm talking about the mitigation, which involves a lot of science, because one of the aspects is to better understand those objects scientifically, physically, compositionally, and this is what I think is the most exciting for us. So first of all, I would say that something really exciting is that from the telescope from the ground to space missions, we went from seeing these objects as light points to real geological worlds. And effectively, the first images that we got from a space mission revealed that these objects are not just boring space rocks. They are really complex geophysical worlds, which can have a wide diversity of sizes, of shapes, of morphologies, of composition, of course, and everything. And you can see on the left various examples of asteroids. Moreover, we saw also that even on one object, we have a wide diversity of geological structures. We can see landslides, we can see craters, boulder fields. Some particles are sometimes naturally ejected. We have boulders of various morphologies on one object. We have ridges, ponds, etc. So this is really striking, because that tells us that they experience a lot of processes during their histories, and we need to understand these processes and how the body reacts to those processes in order to understand the signatures that we see now, which are the outcome of their evolution. So if we want to trace back their evolution, we really need to understand how these processes transfer them with time. And this poses various challenges, because, of course, for space missions, one of the challenges is that they are very low gravity bodies, so you cannot go easily into orbit around them. This is everything is very sensitive. And then also what we learn, which poses a challenge for the design of missions that aim at, for instance, taking a sample or deflecting them, is that you cannot rely on images to understand their mechanical properties and how they respond to an external action like a sampling device or deflection tool. And this will be shown just after this slide, where you will see that despite the fact that some surfaces look like solid surfaces with boulders, in principle, a boulder has strengths, once you touch the surface, sometimes you don't have any reaction, like if you encounter a fluid or a purely cohesionless sand. So it's very important to really realize that images do not tell us everything about the mechanical response of these bodies. And one example is given by Hayabusa 2. So Hayabusa 2 was a fantastic mission, and you got already a seminar by Professor Seguta about this very successful mission, which basically came after Hayabusa, which was, for me, a success, but of course had a lot of problems. And this shows actually that it's worth taking risks, because you start a mission, you don't do everything perfectly, but then it allows you, by the lessons learned, to launch a few years after another mission with even more complex operations and entirely successful. So I think that's a great example of how we can do things a little faster by accepting more risk. More risks equal more missions, and eventually more success. So this mission was really an adventure, and I'm going to show you one example of a counterintuitive behavior of the surface of asteroids. As I was telling you, the images do not tell us all. And this is given by the impact experiment that was done by the Hayabusa 2 mission on the asteroid Ryugu, which is about 900 meters in size. So there was a box that was deployed at 100 meters from the surface of the asteroid. And when the box exploded, it gave energy to a projectile of 2 kilograms that made an impact at 2 kilometers per second. And the outcome of this impact was a crater of 15 to 17 meters, which is very large compared to the prediction by the simulations, assuming that the surface was solid. And in fact, the only way to explain this large size of the crater is if we assume that the surface has basically no cohesion. It behaves like a cohesionless sand, like a sand that if you take it in your hand and you just let it go down, all the grains separate together. And on this image here, this fantastic movie made by another camera, you can see even the impact taking place. It's really amazing. And you see the ejecta, many of them come back on the surface, despite the fact that the escape speed is only 20 centimeters per second. So all this was not captured by our simulations. And all this tells us that this surface is very weak, which is very counterintuitive, because if you see the impact point before the impact, you see solid things. And it's actually more complex than what I say, because you can see that this boulder was displaced, so it did not behave like a cohesionless boulder. This boulder was also revealed, but yet globally, the surface behaved like a cohesionless surface. So you can see the complexity we have to deal with when we try to understand the mechanical response. We have a global response and very locally a different one. So that can cause big challenges for the proper design of missions that want to interact with these bodies. And we are learning how to do that thanks to this kind of experiment. Another success was done by the OSIRIS-REx mission, which comes back with its sample in September of this year. It's absolutely fantastic. We expect to have a few hundred grams of samples. That's really amazing. And it went to see the asteroid Bennu, which is only 500 meters in size, as you can see on this image. And here again, the cameras of OSIRIS-REx were amazing, and OSIRIS-REx went into orbit around Bennu, so made very close flybys, which allowed us to get these fantastic images, which really show how complex is the surface of an asteroid despite the low gravity. You have a wide variety of boulders. You can see black boulders like cauliflower morphologies, more angular one, maybe more brittle, and everything put together to make these asteroids. And you can really see here that interacting with the surface is far from just being on a beach sand around Nice, which is actually not made of sand, but of boulders too. And so this is really something that for us is super exciting, but of course for the engineers pose a large number of problems to make a proper design. And here again, when the sampling operation occurred, you see this sampling tool, when it touched the surface, there was basically no reaction. Again, like for Ryugu, like if we were encountering melted butter, if you will. So very weak reaction, very low cohesion, even an underdense surface, which was not what we could expect by seeing the image before the sampling operation. And when you look at the images before and after the sampling on the sampling site, again, it's a little more complex, although globally it behaved like a very weak surface. You still have some boulders that are displaced, so you have also locally some strengths. So thanks to all these already past missions, we understand now that, okay, these bodies are really interesting because they show us reactions that we didn't expect. This is also because they evolve in a very low gravity environment. And of course, our intuition is based on what we experiment every day on Earth in the Earth's gravity, which is much larger than this microgravity level that we have on an asteroid. So very exciting. And that effectively poses challenges for deflection missions because we need to understand what happened when instead of trying to take a sample, we really want to push an asteroid from its trajectory. And this comes to this first deflection test that we did that effectively rely on a technique based on an impact at high velocity, 6 kilometers per second on an asteroid, and which is the DART mission by NASA, which will be followed by the ESA Hera mission, which will launch next year. So I'm going to tell you about the story of these missions, because I think it's fascinating to realize what I'm going to show now, that everything started actually in Europe. So even though DART was done by NASA and was fantastic and super successful, the idea of a kinetic impactor, the first study happened in Europe when ESA solicited a few of us to form a panel that recommended as a priority a mission called Don Quixote, which was studied in phase A until 2007, and which involved two spacecraft, a projectile and an orbiter. So the aim was to have a projectile shooting on an asteroid and an orbiter characterizing the properties of the asteroid and observing the impact and measuring the deflection to see if effectively this technique, not only we are able to do it, and you will see the challenges with DART, and whether it is efficient. So you can find actually this report on this website. It's free for download. And so that was really the first time we studied that. And unfortunately, at ESA, there was no program or budget associated with the development of this mission. So we went into a desk. And in 2011, I talked with an American colleague, Andy Cheng from APL, and then a few other ones. And we came with the idea that it would be good to make a rebirth of this concept, but maybe this time to save a cost, to share the effort between two agencies, NASA and ESA. So NASA would do the projectile and ESA would do the orbiter. But we wanted that we don't rely entirely on the two spacecraft to get some information, because, you know, the two agencies can have different programmatics, and we didn't want that one agency depend too much on the other. And so the way to make this happen was to choose a target for which, even if we have just the projectile launched, we could get some information. And then on the other hand, if the projectile is not launched, in any case, characterizing the physical properties of a near-Earth asteroid is part of the roadmap of planetary defense. So both cases, if one of the agencies do not follow the other, we could do something. So the critical part was for the projectile. How can we measure a deflection without an orbiter to help? So this is where we came with the idea to take a binary asteroid. And instead of shooting on an object around, or on its trajectory around the sun, we would shoot on a small moon of an asteroid and try to deflect its trajectory around the primary body. And if we do that, when the binary system come close enough to the Earth, with ground-based observatory, we can measure the orbital period of the secondary before the impact and do the same after the impact. And the change in the orbital period tell us whether we could effectively deflect the asteroid. So, of course, with this, we don't have the whole information. We just know that we were able to target well the asteroid and measure and make a change in the orbital period. As you will see, it doesn't answer everything, but at least it tests the technique itself. And so that's how we came to choose Didymos, which is a binary asteroid with a primary body of about 800 meters at scale with other buildings, and Dimorphos, the small moon of Didymos, called at the epoch Didymoon, which was estimated to be 163 meters at the epoch, about half the size of the Eiffel Tower. But be careful, because here you have a sort of an image of the body, but in fact, from the definition of the mission to the final minutes before the impact, we only knew the size of Dimorphos. The shape of Didymos was given by radar observations, but we didn't know at all the shape of Dimorphos, just the size, and even the size was not totally perfect. And therefore, one of the challenges was to make sure that DART, the spacecraft, would be able to shoot on a body for which we only know the size to start with. So this is basically the concept. You have a Dimorphos evolving around Didymos with an orbital period of 11 hours and 55 minutes. And then the aim was to find the right date so that we do it at a time when Dimorphos is close to the Earth and we can have a ground-based observation to measure the outcome of the impact in terms of the orbital period change of Dimorphos. So that was how we started the study. We found that Didymos was coming close to the Earth in September 2022. We were in 2011 when we started the discussion. 11 years is still challenging for some space agencies to build a mission, but we thought, okay, the timescale could match. And we started a study with various colleagues of a mission concept that led to this asteroid impact and deflection assessment cooperation, which combined the development and data interpretation of the ESA mission, which at the epoch was called the AIM for Asteroid Impact Mission and not Hera as on my shirt, and the DART mission. And that's how we constructed this IDA cooperation. And that was in 2013, so exactly 10 years ago. Then the first concept was this AIM mission was supposed to launch with DART independently, but same epoch, arrive before DART, like for the Don Quixote concept, characterize the asteroid, then go at distance, let DART make the impact, and then come back to measure the outcome of the impact. So that was great because we'd be on the same time at the object and do the whole work together. Unfortunately, this mission was proposed at the Ministerial Council of ESA in 2016, and despite the support of many delegations, we didn't get at the end of the ministerial the budget to go for approval and development. And that was a great disappointment. The ESA DG even made a blog saying that he was super disappointed. We were really crying, I must say, because it was really short, and many of us wanted to give up. I didn't want to give up because I saw that the delegations, some of them were super enthusiastic. The journalist called me all night after that with their surprise. Many young researchers also expressed their disappointment. And I really thought about them. I said, no, we cannot give up this enthusiasm, especially for the young people. So we went back to discuss with the ESA director, and he gave us the chance to optimize the mission in order to propose it in 2019 at the next ministerial, which occurs every 3 years. And we did so, and this time we succeeded. And so that's really fantastic. But of course, with a drawback, which is that we could not launch to be in time for the impact of DART on Didymos. And so the launch will be 2024, which will make Hera arrive, and I will talk about it a little later, at the end of 2026. But as you will see, for what we want to measure, it doesn't change, fortunately, much. We can still reach the objective we wanted to reach. So we just have to wait and make more effort, a little more to develop the mission, but that's fine. At least we saved most of the things. So the new scheme, actually, of this IDA collaboration is DART arriving first and Hera arriving after. What is good is that before DART made the impact on Dimorphos, it released an Italian CubeSat 2 weeks before the impact, which could allow to get images of the few minutes after the impact and therefore get some of the properties of the material ejected, which was missing now with Hera arriving late. So thanks to this CubeSat, we could save part of the information and the only information we were losing by not being there on the same time. The only thing is that we know, and we have seen with Hayabusa 2, that a crater in a low gravity can take hours to form. So because the Herschel cube is passing very fast Dimorphos after the impact, it could only observe the first minutes, which is not enough to see the final outcome, but still very important to have the first information of the material ejected, which is very good for the modelers. So this is the final scheme that we have. The DART spacecraft itself is about 600 kilograms at launch. It's like a washing machine with a deployable solar panel, which are kind of very long. And the main payload is a camera called Draco and the smart navigation system, because as you will see, at 4 hours before impact, then everything becomes autonomous. We are at 6.1 kilometers per second, and therefore, with a joystick at 11 million kilometers from Earth, you cannot play with your spacecraft and guide it. So that was one of the challenges, is to make sure that this autonomous navigation works well, knowing that, as you are going to see, we see Dimorphos, the target, at the very last moment. So this is the scheme of the impact and all the figures. We are 11 million kilometers from Earth. Dimorphos is eventually 150 meters and 163. Here you have the trajectory of DART with some angle and basically the geometry of the impact. The launch took place on November 24, 2021 in the night at the Vandenberg Space Force base in California. It was a beautiful launch, no cloud, nothing. It was absolutely fantastic. And it was what we wanted, which means that we launch from Earth at a given epoch, and then we make sure that this launch and trajectory of DART is such that the impact takes place when Didymos, which is here, it has at the closest distance from the Earth. So, of course, celestial mechanics allows to calculate that in advance and make sure it happens. So with the launch on November 24, 2021, we knew that the impact would take place on September 26, 2022 at 11:14 p.m. Standard time. So it was absolutely perfect and at the closest distance to the Earth. Then this is the first observation of Didymos by the Draco camera. So that was about 1 month before the impact. You can see that Didymos is still a light point. These bodies are very small. You need to get very close to start to resolve them. So, but at least we could see that, okay, we detect Didymos, we are on the right trajectory. And then everything happens, as I say, in the last 4 hours. At 4 hours, we start the smart navigation system, so autonomous navigation, and still, Didymos is only a light point. Then you have to wait a little more than 1 hour to start to resolve Dimorphos, which is just 1 pixel. And then it's really at the last minute that you discover the new world that is Dimorphos, for which we had just a mathematical model before getting there. So we are really excited and craving for these new images that would reveal what really Dimorphos looks like. So this is, again, 4 hours and 5 minutes before DART impact. We are at 19,000 kilometers distance. Then we approach 73 minutes before we start to see Dimorphos, just a little more than 1 hour before impact, if you can imagine the excitement. Then we have to wait a little more, 50 minutes. This is a crucial point where DART has to lock its trajectory to Dimorphos. So autonomously, it's very challenging because most of the brightness comes from Didymos, and DART has to choose properly Dimorphos and lock to it. If we miss this crucial step, we know it's finished. We will miss the target. And this is a movie showing you what happened during the final 5 minutes accelerated. And so 5 minutes before impact, they are still very small. So you can see that the images where we see many things happen at the last moment. So here, the DART tried to locate some illuminated points as a reference and try to basically lock on Dimorphos. These images are not linear. The movie is not linear because, of course, the thrusters readjust to make sure that we have Dimorphos in the correct direction. And then we accelerate, and little by little we discover, so we pass Didymos, we don't see it anymore. And then we go on Dimorphos, little by little we approach, and then, wow, we see that we have so many boulders despite the very low gravity, very, very interesting geology. And then the last image at 1.5 seconds before impact, we don't even have time to get everything down, so the rest is blue. And I can tell you that in the operation room, everything was screaming, excited, and I have a movie with that, and it's totally crazy. And these are the moments for which, the reason for why we do all this, right? So this is again the same movie. I won't repeat it. This is the last image we have where we have the full Didymos into the frame and Dimorphos on the left. And already the shape of Didymos is not exactly the one we expected. So which is again exciting. It's like a top shape, a spinning top, but unfortunately, we don't have the other side, but to try very hard to characterize these geological features. It seems to be very smooth at the equator. We seem to see some craters, maybe some boulders. So this tells us about the history and possibly how the binary system formed, because our current understanding is that binary asteroids form from one asteroid, which experienced spin-up due to a thermal effect called YORP. And when the body spins up, it loses mass, which will accrete to form a secondary. This has been modeled, seems to work, but okay, we need to verify these models, and we have different ones. And so, like detective, we try to understand what we see on these images that could be smoking guns about what happened in the past to form a Dimorphos. And then we have these amazing, spectacular images of Dimorphos, which show that it's actually an elongated object. It's an oblate shape, not a prolate shape. And for some reason, normally for forming a binary, you expect a prolate shape. Here it's oblate, like Smarties, you know. So very, very strange. And a lot of boulders everywhere. So now people are trying to characterize the morphology of those boulders, identify some cracks, try to see whether there are craters on Dimorphos. So there is a huge work done even with just these images to try to understand what we see and to infer also the internal properties. Is it an aggregate, like an aggregate of boulders held together by gravity, as our models of formation of binary tell us? Or is it a monolithic rock surrounded by gravels? That we don't know. And of course, it has implication on our interpretation of the Dart impact. So try to do with these images some efforts to better understand. And it really shows that even with just a few images, you can do a lot of science. So this is an image, a mosaic, which has high resolution close to the impact point. We could even give names approved by IAU of percussion musical instruments, of course, which we tapped on an asteroid. And here are some interesting boulders which surround the impact point, because we could characterize identify where exactly we impacted on Dimorphos, and even identify the geometry of Dart before impacting, so you can see where exactly it happened, which makes the modeling of the impact complicated, because you see here the geometry of the spacecraft, the solar panel hitting first these boulders, and then the main spacecraft exploding in between. So to reproduce that in a model is not that simple. You can see here exactly how it happened. And it's not like hitting a flat surface and just see what happens. Here again, another mathematical model. In parallel, in order to measure the orbital period change, we had a wide campaign around the world of telescopes, observations by telescopes, which was absolutely fantastic because the coordination worked perfectly. People communicated together, they didn't know each other, and we could measure the orbital change very quickly from different continents. As you can see, even in Antarctica, we have a telescope from the Côte d'Azur Observatory that is there, in Chile, in Kenya, La Réunion. I mean, it was really amazing. And even in space, because we had the Hubble Space Telescope, the James Webb, and the Lucy mission that is going to see Trojan asteroids that also observe the impact. So there was really a worldwide observing campaign that turned out to be as successful as we wished, and even more than I was even thinking. And the first image we got just when we were out of the operation room was this image, which basically showed the increase of brightness due to the impact, but also a lot of dust. And I can tell you that some of us were super scared that we destroyed Dimorphos. Because, wow, when you see that, you know, so I was thinking, oh la la, maybe we don't have any Dimorphos anymore. That's a little scary. Fortunately, radar observations later on showed that there was still something existing around Didymos. Of course, we don't have an image of the aftermath of Dimorphos, so we don't know really. But we knew something was there. And then we have this spectacular image from the LISHA-Q CubeSat, which shows that effectively we highly damaged Dimorphos. Unfortunately, we don't know what happened afterwards, but first of all, the Dart impact was successful. The autonomous navigation worked perfectly. We shot correctly on Dimorphos. Second of all, we did something to Dimorphos. We don't really know what. And third of all, now we need to understand how much we change the orbital period of Dimorphos, which will tell us something about the effect of the Dart impact. And that was the effort made by the observation from the ground. From space, we had for the first time James Webb and Hubble pointing together at the same time on the same object. And you can see here images by Hubble and James Webb showing the increase of brightness of the system. Several days later, Hubble made also this observation showing you that actually we generated a new comet. You have two tails expanding at several tens of thousands of kilometers, which are due to the material ejected by the impact and the solar radiation pressure that push them away. The reason of the two tails is not well understood, but it shows the same kind of characteristics as comets or even active asteroids. In the main belt, we have some active asteroids which look the same. And in fact, these dart impact tell us that possibly for these ones, it comes from impact. So it's good because we can relate an artificial impact to actual impact in the main belt. And then even later on, February, even March, we still have this tail, which weaken with time, of course, because the ejecta are going away, but show that we generated a lot of material from this poor Dimorphos due to the dart impact. And then we measured the orbital change. So as I said, the first, the orbital period was 11 hours and 55 minutes. So that we knew for a long time before impact. And then after impact, there was a campaign which showed that we basically modified the orbital period by about 33 minutes. We reduced the orbital period of Dimorphos by 33 minutes, which is kind of big. It's not a full surprise because we played with the numerical models, impact models, and we found that depending on the structure of Dimorphos, we could effectively deflect it by a few minutes, but up to a few tens of minutes. It's of course not what was for us most likely, but it was not impossible. So we knew that could be possible. And you can see it here in the light curve that was done, where you have effectively the decrease of brightness occurring here instead of here. So showing that effectively we reduce the orbital period of Dimorphos. And we also increase the brightness due to the ejecta because 96% of the reflected light before impact is due to Didymos, and then 2/3 of the reflected light is due to Dimorphos afterwards. So in fact, what we want to measure is how much momentum was transferred to Dimorphos. So, and this is very important because it tells us the efficiency of the technique. The orbital change is one thing, but the momentum that is transferred is really what counts. Why did we decrease by 33 minutes? Is it because Dimorphos is light and it was easy? Or is it because we ejected a lot of material and therefore we are very efficient? And for this, we need to measure the mass of Dimorphos because it depends on the mass. So let me just explain in a few words. So if you carry a projectile, you shoot a projectile on a target, at minimum, you transfer the momentum of the projectile to the target, which is its mass times its velocity, right? That's the minimum. Then if you shoot on a target and you generate material, the momentum carried by the material in the opposite direction to the impact by conservation adds to the momentum of the projectile. So the more material you eject in the opposite direction, the more you deflect. This material acts as thrusters, if you will. So the key point is to understand whether we effectively generated a lot of material and how much we multiplied the momentum brought by dart itself. And this depends on the amount of material and on the mass of Dimorphos, which we could not measure. So our prediction is that we multiplied at least by 3 the momentum of dart, but that makes an assumption of the mass of Dimorphos that we don't know, and that's why we will need Hera, as you will see. So in fact, depending on the real mass of Dimorphos, we could have multiplied the momentum by a factor 2 to 5. So we multiplied for sure, so it's kind of efficient, but you see that the real efficiency needs another mission to really be precise, because that's very important to really interpret correctly what happened with the dart impact and what we can really do with an impactor of 530 kilograms at 6.1 kilometers per second on a 150 meter body. So we still have a big uncertainty. Moreover, what we try to do is to understand what is the final state of Dimorphos. And this is kind of complex and challenging for numerical models, because you can see we have to model a body which has a lot of rocks for which we don't even know the strengths. It's not flat at all. So we have to model that correctly. And for now, what we find is that we could have left a crater if Dimorphos is robust, is solid, or we could have totally reshaped Dimorphos. And the data of dart allow the two possibilities. So there is no possibility to conclude on that. And that's important to know, because we need to validate the numerical models at the correct scale. And for this, they need the final outcome to be validated. And you see here the current efforts that are done numerically. And this is where Hera will come into play. So we had dart, which was extremely successful. We have the cover on Nature, the many paper, all open access, so you can download them easily. And a large international collaboration. This is close to the operation room at APL. Many young people, which I think is really great. Many women also, which is also very important for us. And everybody is participating to this effort, which I think is really fantastic. The next step is a Hera mission, because this is really Hera, which will answer the remaining crucial questions to have an unbiased interpretation of the darting path and make sure that we can extrapolate this knowledge to other scenarios. So one of the key questions is, what is the final state of Dimorphos? Did we leave a crater? Did we reshape Dimorphos? This is very important to validate the numerical models. What are its properties? Is it a rubble pile? Is it a monolith covered with gravel? This is also important because the impact response depends on the structure. So we need to understand whether the response that we observe was due to the fact that it was a monolith or rubble pile. It has different implications. And then what is the actual momentum transfer by the impact, which needs the mass of Dimorphos? And for this, we have now the Hera mission, which is now in integration for launch in 2024 by Falcon 9 from Cape Canaveral on October 8th nominally. So we are working very hard to be ready, and you will see some images of the spacecraft. We have an international workshop open to everyone at TestTech in October, where we can make a visit of the Hera spacecraft, which will be there for final test. So very, very exciting. And then the scenario is a launch, as I said, in October 2024, a cruise during which we will make a flyby of Mars and make Didymos observations, so one of the moons of Mars. And then we arrive at the end of 2026 for 6 months of close proximity operations with many firsts, because this will be the first rendezvous with a binary asteroid, the first investigation with deep space CubeSats. One of them will carry a low-frequency radar that will probe for the first time the internal property of an asteroid, doing radar tomography, and many, many other things. So this is a spacecraft, 1.2 tons. You can see the dimension, the radiator, the solar panel, the thrusters, the fixed antenna, etc. All the dimensions. The payloads are these 2 CubeSats, one devoted to the geophysical properties of the objects with a low-frequency radar, a gravimeter, because it will land with this CubeSat on Dimorphos, and we can then do gravimetry and radio science to have a complete understanding of the gravitational field of the asteroid, which is very important. And then we have another CubeSat, Milani, which will do a mineralogy and also a dust detection and analysis and radio science. In addition to these 2 CubeSats that will be deployed at closer proximity, we have onboard instruments. So we have 2 framing cameras. We have a thermal infrared imager provided by JAXA. So we have an international component with a Japanese contribution. We have a laser altimeter. We have a multispectral imager. We have a monitoring camera that will observe the deployment of the CubeSats. So all of this will allow us to fully characterize compositionally and physically Dimorphos, and also, of course, Didymos. And radio science experiment, of course, for the mass, which is also a crucial component. You can see here some images of the integration. So it's good to see the baby growing up with the propulsion module, the core module. And here you have the propulsion tested at Avio, propulsion module, and then the core module at OHB in Bremen. So everything is taking shape, as we say, and we are all very excited to see this happening. So we have a mother CubeSat with a mother spacecraft with 2 CubeSats. The CubeSat, the advantage, we can take more risks, we can go closer. It's a more rapid implementation, although these are complex to design. We should not minimize that, because they have to have their propulsion module and everything to be able to navigate. So, but it's very exciting. And then we'll have the first detailed investigation of a binary asteroid. With many, many aspects I don't have time to develop, but basically we can study the geophysics of a fast spinning body, because Didymos rotates at 2.26 hours, and we realize that depending on its level of cohesion, it may behave totally differently if it's, for instance, spun up. You can see various images where we differ only by a few pascal the cohesion. 1 pascal is the equivalent of the pressure of a leaf on my hand, and we are sensitive at the level of a 1/10 of a pascal of an asteroid, on an asteroid. So that's why I say it's counterintuitive, because for us, solid, weak is kilopascal. No, on an asteroid is 1/10 of a pascal, so totally different. Then the first geophysical data on an object which is very, very small, much smaller than anybody visited so far. So we can see how the processes scale down to this level of gravity. Then we have the first internal probing of an asteroid with a radar tomography. We will be able to measure the level of heterogeneity inside Dimorphos, which is important for the binary formation model, but also for better interpreting the response that he had to the DART impact. We also have mineralogical study. We can measure maybe the interior of Dimorphos if it has been revealed by the DART impact, whether it is homogeneous or not. Maybe there are some exogenous material like we found with Hayabusa 2 and OSIRIS-REx on other asteroids. We can see whether there are still dust present in the system, either due to micrometeorite impact or even mass shedding for Didymos, because Didymos is rotating fast, maybe it still lose mass. So many interesting things and possibly new surprises. And finally, the first landing on a CubeSat on such a very small body. With this CubeSat, we'll have accelerometer, so we can measure the bouncing coefficient. And that, as I said in the beginning of my talk, we need to touch in order to understand these bodies. So this is really interesting. And we have various operation phases, more or less distance. So it will be really exciting. And the operation team at ESA works very hard to make sure the operation allows us to do the science we want to do and answer to all the questions we want. So this is for Hera. We are getting prepared. We'll have a lot of excitement. And for the last 1 minute of my talk, I just want to say, because we are doing Game Changer seminar, that we also need to change our approach to do missions to be faster. And that's really my claim, is that we should be able to do better. And one possibility, one opportunity to do that is going to see Apophis in 2029. Apophis will come at 31,000 kilometers from the Earth, very close distance. We will see the light of the body with naked eyes from North Europe, from West Europe and North Africa. So 2 billion people at minimum will be able to see this object at naked eye. And I can imagine a child to whom you say, you see this light point in space, you can see the light, there is a small robot around trying to understand it. He will remember it for his whole lifetime. So if not for science, for educational reason, this is a great opportunity to mount a mission. So the OSIRIS-REx will arrive at Apophis after releasing the sample to the Earth about a few days after the encounter. And what we would like is to have a mission being there just before the encounter and observing the closest approach to see if tidal forces with the Earth can move the surface. This is another way to see how to interact with an asteroid and how it reacts to an external action. And for this, we have an opportunity to demonstrate a faster approach, which is to use an already existing platform. In this case, would be Hera, for instance, or another one that could go to see Apophis, noting that we have to launch in 2027, so very close to now, 4 years. So we have to go fast. And we have this concept, Ramses, studied at ESA in order to be able to do that. And that would also respond to a request by the Decadal Survey of NASA, which for the first time has planetary defense in its report, and that asks for rapid reconnaissance missions. So we hope we can do something in Europe. There is not only ESA working on that, there is also CNES and JPL working on another concept with two CubeSats and two CubeSats and one mother spacecraft to do a bistatic low-frequency radar, again, probing the internal properties before, after the encounter, which would be fantastic, both cases. And any mission before, with synergy with OSIRIS-APEX, we know we have another mission 8 days after, looking at the aftermath. So having a mission before would be fantastic also for the international cooperation. So we are working on that and hope this thing will happen. And this is finally my conclusion that, okay, we are in good shape to launch in 2024 with Hera, which is great. We'll answer many questions. And exploring these new worlds is fascinating and a source of amazing feelings and surprises. So that's why I really want to involve more and more people in these adventures. Working also with engineers and scientists together is also very important and allows to save a lot of time when we have direct interaction, because they know about the science we want to do. We know they're constrained in terms of design, and that's really important. The same using of CubeSats and taking more risks, I would say, is really important. I think it's okay to fail as long as we learn and we can build more rapidly another mission and do more science. And Hayabusa 2 are great demonstration of that. And of course, international cooperation is fantastic for many reasons, as well as, and this is very important for me, the involvement and education of young generations. I mean, the excitement we have in these operations rooms, we cannot just keep them for us. We need to make the possibility for the young generation to get this kind of experience, because that allows also you to have a spirit, the taste for challenges, and you can really tackle challenges and solve problems in a way that you cannot do without this kind of motivation. And I just finished there just to show you the coming missions to asteroids. And you can see that the yellow ones are the ones that are going to fly. We have really an era that is fantastic for asteroid missions. Even the Emirates are doing a mission to 7 asteroids. And then we have these blue lines, which hopefully, I hope, will fly because we need to go to see Apophis. And with this, I thank you very much.
Applause, Patrick, for this inspiring and fascinating talk with lots of interesting results, like, for example, using CubeSats as real science companions. Yeah. So let's have some questions. I see there are already lots of questions. So if you do have questions, please write them in the chat and we'll go through them right now. And I will ask the people if we have enough time to unmute their microphone and speak up. So the first in the list is Ludwig Klein. He had a talk about the material falling down. Ludwig, are you able to speak?
Yeah.
Yes.
Thank you very much. Good afternoon. Thank you for the talk. I was puzzled by your initial comment that you said the escape speed of, I don't remember which body, was 20 centimeters per second, and yet you saw lots of material falling down. What does it really tell you, this observation?
Yeah, so it tells us that the crater formation is dominated by the gravity, despite it is low, of the body and not the strength. So if you shoot on a cohesionless surface, the ejection velocity will be much lower than the ejection velocity of material on a hard surface. Therefore, that tells us, like if you can do the experiment and to shoot on a solid rock, you can see that you break it and material goes away. If you go in a sand, you can just bury.
Okay, thank you. Yeah.
And the problem is that we cannot see that in experiments because the velocities are too low compared to Earth's gravity, I mean, in experiments on Earth. So we cannot capture in experiment the low velocity component of the ejecta. And this is the same in modeling, because in modeling, these low velocities are almost already in the numerical noise of the model. So that's why I say it's really challenging to model these objects, because their low gravity is make them behave in an environment that we cannot capture easily experimentally on Earth and in models. But that really told us, both the large size of the crater and the low velocity of the ejecta, that we know we have two regimes in cratering: the strength regime, where the strength of the material is what controls the crater, and the gravity regime, in which the gravity of the body controls the crater. And we were in this case, which means the strength doesn't matter.
Thank you.
Okay, thank you. So next we have William Woe. William, you had several questions. I guess the one on the orbital period has been answered. If you can, you're unmuted.
Yes, hi. Can you hear me?
Yes, it's not so loud, but it's okay.
Yeah, you can ask your question.
We don't hear you anymore.
Did you lose me there? I think you lost me there. Yeah, okay. Anyway, so Carl Sagan in the pale blue dot, I think it was, I was worried about asteroid deflection technology being used by terrorists. I mean, do you think about that? Do people wonder about that, or?
Well, with terrorists, they would first have to do all the steps we are doing, and we would see it. So it's not really terrorist, but effectively we have to make sure that this planetary defense topic is not used as an excuse, let's say, to make new weapons, let's say. So first of all, the military people are not really interested, because the budget that we need for planetary defense is in the noise of the budget that the military people get. You know, the DART mission was $300 million, and the aircraft carrier is $2 or $3 billion. So that doesn't really work for that. However, we still have to be careful about, you know, because sometimes we invoke the use of nuclear bombs in order to deflect an asteroid in case of very big asteroid. And this is why we have this working group under the United Nations that try to coordinate an international response, which is agreed by the various space agencies that can implement a mission, so that we mitigate this risk. Of course, there are no world authority, even the UN, but we hope that if we have a robust protocol that we demonstrate can work, this is the one that will be used and not something very arbitrary or improvised. So we are careful about that, but I'm not worried by you know, a country or a terrorist group doing that, because you cannot do that. You know, you need preparation. It took us 20 years to do these missions, okay, because we needed the budget that took the most of the time. But you still need to make some tests, etc., and we would see it. So I don't see it happening, but effectively this is a kind of thing where we have to be careful about what we do, and we are aware of this, and this is why it is good that it is also in the end of scientists working with agencies, and also why not the army, they can have some interest, and this is not bad, but everything under control, so that we can, let's say, keep some sort of control.
Right, thanks.
Okay. So we move on to Steven Spengler, another familiar name in this series. So Steven.
Okay, thank you. Can you hear me, Terry?
Yes.
Okay, good. Well, thank you. I enjoyed that talk very much. I have kind of, I guess, a negative question. I guess you would call it Spenglerian pessimism, to use a philosophical term. At the beginning of your talk, you said that asteroids would be our best tracers of the formation of the solar system. But my understanding is that some of the large asteroids, at least, show evidence of geological differentiation, and the collisional processes are very important in asteroids as well. So these small near-Earth asteroids, I would tend to think, would just be conglomerations of pieces from all kinds of different asteroids with different geological histories. I think the geological term breccia is what you use for these collections of fragments. And so they might have very different isotopic signatures. And so I'm skeptical that they would provide the kind of information you were implying, as opposed to comets. There really do seem to be pristine objects. Now, it's easier to get a spacecraft to a near-Earth asteroid than it is to most comets. But still, how would you respond to that skeptical comment?
Yeah, this is a very legitimate question. Actually, when we propose a sample return mission to space agencies, obviously this question is asked because it's not intuitive. So effectively, the big objects, some of them have been differentiated, although the first only evidence is for Vesta. So they were heated and transformed, and maybe some of the record of the composition is lost. For the small ones, we have to make the distinction between the primitive aspect of the material and the primitive aspect of the structure of the body. So of course, these near-Earth objects are the outcome of catastrophic disruption in the main belt. And when this happens, you have a lot of material that is ejected and reaccumulating to form these rubble piles. So they are not pristine in the sense that they were not there when the solar system was formed, I mean, as they are now, but the material was there. And what we found in collisions is that in the impact energy that are involved in the main belt, you don't eat much the material. And therefore, you keep the original composition. You don't keep the structure, you don't keep the same bodies, but the composition is not transformed over time. And this is why we can target an NEO to get the most pristine, the oldest material that we can have. And in fact, the samples returned by Hayabusa 2 confirm that. We have Hayabusa 2, the sample has the same composition as the most primitive carbonaceous chondrite that we have on Earth, which is a CI chondrite. We could even identify hundreds of amino acids, even uracil. So all this was not lost at all in the processes that the body underwent geologically during its lifetime. So the answer to your question is effectively, we have to make the distinction between the composition and the structure. Structure is recent. Composition can still, for the small ones and for the small one which come from a parent body, which was also not differentiated at first, then it reflects the original composition of solar nebula. We find chondrules, we find all the things that are really the oldest material that we have on Earth. And we also have hydrated minerals, which shows that they don't lose hydration, even though they are the outcome of impact.
Yeah.
Thank you very much. That's an authoritative answer.
Okay. We move on to Antonella. Antonella, you had a question about light pollution with Starlink.
Thank you so much for this outstanding talk. It's so fascinating, and your enthusiasm is just so contagious and wonderful. So my question was, I'm fascinated by our collective ability to detect these asteroids from the ground. So I was wondering if you could say a little more about how it's done. And in the future, is this ability going to be hampered by the presence, now we're talking a lot about Starlink, trace in every single image we take, even with the Hubble Space Telescope. So I was wondering if you can provide some comments on this.
Yeah, so in fact, we have two telescopes that dominate the discovery of near-Earth objects, which is the Catalina Sky Survey in Arizona and the Pan-STAR telescopes, which are in Hawaii on the fantastic island of Maui. And they really dominate the discoveries. The amateur astronomers are essential for the follow-up. So many of the orbits are better characterized thanks to the follow-up by the amateurs, because amateurs are distributed everywhere in the world, so we can cover that. And the organization is really good because now we have implemented under the United Nations this International Asteroid Warning Network, so which is a network that is effectively, the aim is to be organized in order that we know an object is coming soon and we want to observe it better, to have a better accuracy in the orbit, and we organize. And in fact, we do some campaign to test this coordination with a few bodies, and we already published a campaign for Apophis, for instance, that allowed, by the way, to eliminate the risk of collision that was remaining for 2068. So before it was 2029, then 2036, then 2044, then 2068. So it's eliminated because we made this international campaign. So we are working hard to do this campaign to make sure that we have a good communication, a good organization, and the DART impact observations really demonstrated that people, but the amateurs is really fantastic because they know where to put the information at the minor planet center. So if you want, when you have an observation, immediately you send the ephemerate to the minor planet center, and then this database is used by two independent operation centers, one at ESA, one at JPL, that compute automatically the impact probability of the object. And very often, the first impact probability is high because the orbit determination is poor. So you have many solutions leading to the Earth. And then we put that, we are very transparent. It's written on the website. Now the journalists understand that they have to be careful when they see that the first day doesn't mean anything. And then the people observe more, we improve the orbit accuracy, the calculation is redone, and until now, the impact probability has always decreased to 0. So that's how we do that. In a transparent way, because we have to make sure the amateurs can get the information.
Yeah. Okay, thank you. So we have a double question by Sergei Rudenko. Sergei?
Hello, can you hear me?
You're still muted.
Can you hear me?
Yes.
Okay, thank you very much for very interesting presentation and impressive results. So I have two questions. The first one, what type of observations was performed from the global network of telescopes you mentioned?
So the kind of observation was light curve observations, which was aimed at measuring by occultation, basically, the shadow of Dimorphos passing in front of Didymos or behind. So the decrease in brightness would tell us if you do it before and after, between 2 degrees, you know what's the time spent and therefore the orbital period. So we needed a few telescopes to do that, and it was done worldwide. We had also spectral observations to measure the composition of the object, which was known before, but then it was very close to the Earth, so that could allow to have a more reliable information before and after the impact, because we never know whether after the impact the composition could change. If you revealed something, it's the same. And we had also radar observations. So the Goldstone radar in California was used to have a really accurate measurement of the orbital change, because of course with radar we have a better astrometry. We hope to have Arecibo at the time we built the mission in 2011, but as you know, Arecibo does not exist anymore. Unfortunately, it's a very big loss. So radar, light curve, and spectroscopic observations. And from space, you had the Hubble and James Webb.
Okay, thank you. And another question, you mentioned the third reason why you are interested, or we are interested in asteroids, are resources. My question is the source of which material to be potentially transferred from asteroid to the Earth can asteroid serve?
Yeah, so in fact, originally the people, the miners, wanted to mine asteroids effectively to bring back the material to Earth and make business. But very rapidly, and because I also interacted with them, they realized maybe, at least for now, is not the best approach, because you can see that, for instance, OSIRIS-REx will bring back a few hundred grams, and the mission cost $800 million without the launcher. So it's a very expensive material. Moreover, let's say that you are able to do that, and you have a lot of rare metals on asteroids. You bring them back to Earth. It will remain expensive because space is never cheap. And then you will decrease the price of this metal because it's not rare anymore. So the business plan for that is, we have to see the long term. Maybe space will become very cheap. Already with the private sector, the launcher are less expensive. But on the short term, it's not the best approach. So what is really now under the mind of those people is to see whether we can use the resources of asteroids in situ, so that we can, let's say, rebuild something to go further away. So instead of carrying all the propellant with you from Earth, and more mass means bigger launcher, more expensive, you take, let's say, a less massive spacecraft, less propellant, and then because you have oxygen and hydrogen on these asteroids, assuming that you are able to extract it from the minerals and reduce propellant, you could go further. It looks like science fiction, and I must say that given the complexity of geology, it's not for tomorrow, but it's not stupid. And who could have anticipated that now in a little USB key you can have so many encyclopedias? Even 20 years ago, when I defended my PhD, and in 1997, I was offered a 1 gigabyte hard disk, huge like this. So we can go, but that's the aim. The aim is more to use them as gas stations to explore further the solar system.
Okay, thank you very much.
Okay. So we have a question by Jordi Miralda Escude about exoplanets.
Exoplanets.
Yes, hi. I hope you can hear me.
Yes.
Yes, I'm Jordi Miralda from Barcelona. And I would like to ask, we now know there are these exocomets that we've discovered in the solar system. There was Oumuamua, right, that was discovered and basically flying by through in this hyperbolic orbit. And what's very exciting is that supposedly these are comets that were formed in some other planetary system, somewhere in the galaxy. They were at some point expelled from their planetary system into interstellar space. And then they just wandered randomly through the galaxy and just randomly came across the solar system and fly by the sun. So of course, this offers a tremendous opportunity to try to go there, analyze it. And if we're able to analyze some composition, study the material there, we are sampling a material coming from another star. So my question is, are there plans, people proposing things so that once, we'll have the Rubin telescope that supposedly will discover many new ones of these. Once we can measure them and find one where maybe the orbit is good, we can send a spacecraft there and try to catch up with it.
That's my dream. That's my dream. Effectively, Oumuamua, we call it an interstellar asteroid because it didn't show any activity like a comet, which is still a surprise. there was a slight non-gravitational effect, which we believe we understand. Very mysterious, very interesting. And of course, the comet Borisov, which was bigger and more active, but many remaining questions about those objects. And effectively, they would contain so much information. Now, the problem is that they come very quickly and they pass very quickly close to the Earth. So, and we know it, unfortunately, when they pass close to the Earth. So you cannot build a mission in advance because you don't know it in advance enough. Now, what could be a possibility? So there are some ideas to launch, you know, a solar, no, what do you call that? Sailing, solar sails. Sorry, maybe you push by laser to catch up when they came, but it's very complicated. Another one which could work, but again, the dynamics of these objects are very not favorable for space mission interception, but we have to see, is the Comet Interceptor mission, which is an ESA mission that will launch in 2029 with the Ariel spacecraft devoted to exoplanets, so we have a link, and it will be placed at the L2 Lagrangian point. It's very smart to wait for the first long period comet that will come in the solar system. Because in fact, the comets that we saw, we never saw a fresh comet. All comets that we visited had already a passage around the sun. So we never saw a comet that never saw the sun. Unfortunately, when a comet comes in the solar system, we will know it can come close to the Earth when it passes Jupiter, which is about 6 to 1 year before only. So we cannot launch a mission within this time frame. However, if we already have a spacecraft waiting for it at L2, then we have a deal. And this is a collaboration with Japan also. And the people working on it think that depending on the geometry of the encounter of an interstellar object, we may have a chance also to go to see one of them instead of a long period mission. So there is maybe an opportunity, but of course it would be fantastic.
Yeah, so thanks very much.
Well, Patrick, I think we have to bring this to an end. Although it's a fascinating talk, again, applause. It was fascinating. It was inspiring. We learned a lot. Thank you so much. And to everyone who's still online, I may remind you there's going to be another talk in 1 month from now by Judith Lean on long-term solar activity. So thank you very much to everyone. Have a good evening. Have a great day. And maybe see you soon again in 1 month. Thank you, Patrick.
Thank you very much.
Bonsoir.